Yes, recording in progress. I like transport. All right. Well, good morning, everyone. Today we're going to be working on learning hours of transport phenomena. So yeah, we have a question on the processes of how to approach the questions from homework. Let's see what you got, Paul. Throw it.
Okay, so I guess for 3D,
Reading. Let me look that up really quick. This homework, what? 3? 2? 2. Whoa, what? You have an assignment due on Monday? Interesting. Yeah. 3A. Oh. Okay. Good to know, right?
Yeah.
All right. We are making some progress. You said 3, okay. So we have velocity field. All right. So let's make up some numbers. So 3, 4x plus 4x. Was 4x. So we have the vector. Oh, come on, I thought it worked. Did you work? Velocity. Yeah, velocity it's equal to, let's say, 4x. All right. So we have that vector. What do you want to do with that vector?
So
What are your plans for?
so for 3D specifically, which specifies particle is located at xy of 1, at t equals 0. We want to find the position at t equals 5. So without
Okay. Okay. So you have this vector.
Correct.
And then what do you want to do with it?
I want to, we're given the vector position at time equals 0.
So you have this. So you have the vector with some x and y. And that's gonna give you the vector in that position, right?
It's the position of the location. We're given the location.
Okay.
So we're given that like the xy is 1 at t equals 0.
3, okay. Okay. And then you get a vector, right? So let's see that you get 3, 3. In this case, you got 12. Y squared 3, 9, 9 plus 8 is 81. All right. Right. Something like that.
Yes, I just so for this we're trying to determine the position after 5 seconds.
Okay.
I was thinking that I could use, since we're provided the x component of the vector
Okay.
and the y velocities, I was thinking of
The x, the y, yes. Here, the x, the y,
I was thinking of integrating
Okay.
those vector components with relation to time to find the position.
Okay. So you have this. Say, so you're saying you have velocity, which is
Yeah, we have
12 centimeters per second, 1 per second. And what do you want to do? So you don't have this.
we just have the, I think we're using the equation and I haven't plugged in the so I was using we plugged in to find the like the c constant of the integral.
Yes. Yes.
So what I work with.
Let's
is
try it,
this
because-
variable.
So you get dx over dx is equal to dy over dy. That's what you're saying?
That's for the part A of the question, when you're kind of, that's for close to.
The whole street there.
So what I'm trying to figure out is the position, so we are given the original position,
Yes,
and we want to find the position after 5 seconds.
so you're multiplying times 12. In that case, you're integrating with respect to time.
Yes.
Okay, how are you doing it?
So we're provided the, velocity field.
Okay,
And so I used the x component and y component, and I integrated those with respect to time to find like the x distance and the y distance.
okay. You wanna come to a word and train with this? See your thinking, see if I can challenge. I mean, you're forward, you can be challenged for it, you know? Let's see. So you have that actually? Oh, my bad.
Here you go. So we have this big vector, and so in this situation, we have this initial position P3 time to 0.
Yes,
Let's say they want us to find that time equals 3 seconds.
right,
And so this is what's simulated second.
yes,
So what I did, since we're given the initial position 3,
yes,
that would be used to determine that would be like the initial position of the initial point where it starts at.
okay, okay.
And so that.
Before you go any further, we have right now continuous differential velocity, correct? Yeah, like, position over time is equal to velocity. And we have an equation for that. And when you integrate, yes, you get what you're saying, position, right? So the derivatives of position with respect to time, velocity.
Correct.
Okay. You can define it though, yeah.
And
Like dr dt is equal to, in this case, v or like vector. Okay, that's what you're trying to do.
yes.
All right, I
And
like
so
it. I like it.
I'm using the integral to find the distance traveled from this initial point.
Oh, so you're saying like your initial bound 0, final 3?
Yeah. So yeah, our timer
Okay.
starts here and we start at this position.
Yes.
And so what I'm using the integral for is to see how much we move in the x direction and the y direction.
Like that, like that.
So I integrate both of these with respect to time. So the dx component for x okay.
So you're basically looking for an equation that can tell you in each component how position changes over time, correct? Good.
So this is what my approach was.
I like it.
I have this is the dx component
Yes,
over the time,
yes, over that period of time, yeah.
and then I
Really hard integral, yes.
really vary.
Yeah.
Same thing with the y component. I also do that with respect to t.
Yes.
And then so for the x, for the distance traveled with x,
Are you treating like that as a one, as a variable, or something?
the x,
As a, no, everything. That those integrals, you're treating it as a variable, as a constant, or you
well,
working?
since this I'm integrating with respect to time,
Alright,
this would be basically a constant.
yes, you're right.
So it would be for x t from 0 to 3,
Yes,
and this would be ay squared t from 0 to 3.
yes,
And so since I integrated this, I'm focusing 0 would be 0.
Yes.
This will be 12x, and this will give me It's 24.
Yes.
Pi squared.
Mhm.
And so this would be.
Vx, no, Rx,
Alright.
which is the vector position.
Oh, correct.
You can equate it, like R of X is equal to 12X, and then V of R of Y. Remember, don't forget the hell. Not this, there, that, yeah, yes, because we're talking about vectors. Yeah, love it.
Okay, so we have this.
We do.
And so I'm guessing that in order to determine the distance traveled, I would use the initial points provided. Which would this be that we're given a vector that starts at x equals y, x equals 3, y.
Okay.
And so I would use, so if I can look for this, 36
Yes.
or
Centimeters.
yes.
Don't forget the units. Good, good, good.
And for our y, we have 9%.
Let's say 180 plus 36. So
260.
that's right. And why are these different?
Because this would be the velocity at this position.
Perfect.
While this is distance.
Every time that you work in it, I didn't do it here, but underneath or close to it, but like for example, and I recommend to do it now, Vx, Vy. So when if you have time, I'm pretty sure you will, in the test or in home or whatever, it's really easy, and also for the grader to go over this and be like, oh, yeah, this is exactly what he needs. Yeah. Like over annotating is never enough. So good. All right. So what's going on then?
So now we have this
Initial what?
Well, this, since we integrated over 0 to 3, this is like the distance vector in the x direction and y direction over the second.
Sure. It's not the initial, that's right.
And
The
so
initial is
yes.
all right.
And so in order to determine the final position at 3 seconds here, I was thinking that we add this distance traveled to the initial xy route. So like this would become plus 3, which is the origin is 3 for the vector.
Oh. So you want wait. So if I have this one, and I give you a point here, a point here, I have the next one. That's 2. Y2. What are you looking for? This or this? I'm asking about this. Which I think that's a question, right?
I think it's just position.
That's it. You're saying that that's C, right? It'll be if the particle is located whatever times 0, what is its position? Yeah.
So I'm thinking we start at the answer would be related to the origin.
Yes. Yeah. Well, let me read this. The particle is located here times 0.
Otherwise,
What is its position? Yes, it has to be. It has to be.
otherwise,
Then I'm asking you what's the distance between this point A and point. That's what I thought you meant. No, they're actually looking for.
yes.
So you're looking for.
Otherwise, they would.
It's good. It's good to do this like mental checks all the time. Good. So, continue.
So we would add this. I think about these.
Really hard not to get nervous.
So our X would be 39 centimeters. R would Y.
That's right.
And that would be
The final position. You got it?
okay, then
Uh-huh.
in relation we'll have the next
Question.
next-
The next problem, like
what
E?
is E, or E?
Or
That
E.
would be, what is the velocity of the, okay,
Oh,
so I'm thinking,
uh-huh.
since we evaluated the position, we would plug, these into the original dx dy's in order to get the velocity of that.
You might guess.
And so I guess for that, it would just be,
Wow. We're gonna have like 2 answer keys in that homework. One done by the graduate student, and the other one is gonna be yours. Hello, Gabe. Happy to see you, man. Thank you for coming.
Yeah.
We're working on a similar question to question 3 in the homework. It's not the same. It's a different. It's something that I made.
Yeah.
So we're working on D. Now we're working on D.
Okay.
Let's finish with this, and then you can ask something if you want.
So we'll just do that and then we substitute this number. 39 times 1.
Oh, do you get it? Okay. What do you get? What do you get?
Oh, I got a salt piece.
Oh, peace nugget. Boys getting protein like that. Good. Yeah, I'm hungry, so I haven't had lunch. After this, I have to do some homework, so pray for lunch. It's okay. I'm having fun. I'm just check that we're recording this, because I'll be very disappointed if you have that. Yeah, right. All right. Three. That's okay.
That's
I really,
how.
yeah, that's the way to approach it. Well, at least it's one way that the process looks better. Yeah. All right. Now you have a question, or you have a question.
Yeah, I have a question.
All right, you can go, and then if Paul has another question, you can go. With it.
I guess it's similar question to this question 4.
Question 4. Oh,
Yeah.
okay. Let's see. Ooh, they cannot see. Oh. Wow, that's crazy. Unfortunately, I don't have photo pens. Oh, let's do this one. Yeah, that one I can see. All right. At least I noticed now, not later. All right. So you said question 4.
Yeah.
All right. So let's see. Let me pull that here. I can see what you. So we have for velocity field this. So velocity field. So we have some vector. And the x component, let's say, is. Oh, this is interesting. Because when you're doing the integral. Oh.
Yes, specifically for
Yeah, I think it's that this particular example, I need to come up with a very specific counter example. Huh. Oh, I have. One something equals So 1, 2, yes. So I need a derivative. It's gonna be okay, now let's trust the process. I was doing this specific question with the TA, and it's interesting. Let's see, so say I want it to be over 1 over, I don't want it to be that linear. Let's see. Um, So, no, I don't think it's more actually. So. And then, yes. Nope. Why? Oh. Can you remind me of exactly what the, so that's gonna get 1 over that.
Well, I guess like the issue I was having when
Yeah, what's your,
the part B one, so they're giving you 3 points to you want to streamline to get to those points. But one of the points I saw was for the defined constant.
yes. What does that mean?
I guess like those as you look at your approaches that value it's basically that never reaches there, but it wouldn't stop that point.
Okay, so you're saying that if you have a function, in this case, I think it's average velocity, right?
Yeah, that
The average velocity at some point is giving you an undefined.
or actually I think average velocity is question 5. This is the velocity field.
Oh, the velocity. So we have, let's say 4x minus 4x minus 2, and then the other one is y. All right, we have, all right. So what's your question? Question what? Question. Which one?
It was 4
For B. So how do you get the streamlines from here first? Because I'm pretty sure we need the streamlines for that, yeah?
yes, you want the general equation for that.
All right, how do I get there? From here,
So
what's the equation of a streamline?
yeah, you set it up as dr dv, which is equal to dx over dx,
So the x over dx is equal to what?
dy over dy.
dy, right? So this is streamline equation. Good. Okay, what's dx and what's dy here?
4x minus 2 is dx.
All right,
Dy is y.
so dx over x minus 2, y dy, 1 cube, right? So what do we do now?
So you want to make sure that the anything related back from one side and vice versa for y.
Do we have?
Yeah.
Awesome.
Then you want to basically integrate.
All right, let's do it. Doing this. All right, so we're integrating the streamline equation. All right.
So I guess like the left side the substitution.
Alright. So you some use substitution, what's gonna be my u?
4x minus 2.
4x minus 2, okay. And what's the u?
4 dx.
Yes. Alright. So what do I do now?
So now I'm going to solve dx.
Hello!
Right.
You have a little party going on. I like that. In just a second. So you said, what do we do now?
Solve dx is 0.4. And then,
So this is gonna be you now?
yes.
Alright. So you should go, wait, you said something about the x. What happened with that?
Yeah, you want to solve for dx.
Okay.
So,
So we get the x is equal to the u
yeah.
over 4. Awesome. What now?
Now you can substitute.
Here.
Correct. Yeah, here.
So u we said is this, so this is u. This is u. Okay. So
Yeah, and then.
so
the-
so we get a 1/4 here. Awesome. And what else? Is that it?
Yeah.
Right, so that's what I want to do. What's a little guy?
So now you add of you.
Here. I haven't done anything to this, don't you?
Yeah.
This is a thought. Okay, so now, actually, good. So now we said 1/4 of the land of what?
Of you.
You. Awesome. Just that?
Plus the constant.
Here. Equal to something. 2/1. All right. So that's it.
Yeah, and then I plug in 4x minus 2.
We can get it back, right?
Yeah.
The line of 4x minus 2. Yeah. What's she want? What happened to the other side?
Yes, in that side, you integrate.
Yeah.
Negative.
Remember that this is. Remember that 1/1 to the third is equal to y to the negative third. That helps.
Yeah. So when we integrate that, it would be negative 1/2 y to the minus 2. Or negative 1/2. Yeah.
That?
Yeah.
All right. Just that?
And then you can put like y squared in the bottom.
Yeah. We can do that here. Right.
Yeah.
Like that?
Yeah.
All right.
Then,
So it's not C1 then.
yes, then that's plus.
Or here we can put C2. All right. Then you can do something funny like C1 plus. You can put in either side. So, see, it's into over. All right. So now what?
So now you want to solve for y.
Yes, we have. All right. You get a funny expression actually. It's a little harder than the number actually. Okay, that's okay.
Okay, so
Hold on, you man.
yes. And yes. Swap them.
Yeah. So so y is equal to 4, right?
Yeah, 4.
4x minus 2 little C, and then we have, oh, a negative, right?
Yeah.
All right. Good. What else? We're missing some.
Um,
The two is here. So should be all of this multiplied by two?
um,
Yeah.
yeah,
The bottom. All right. And is that it?
just carry two, make it out.
That's good. Two divided by four x. Minus two plus, okay. Is that it?
Then you say the square root.
That's right. So y is equal to square root of minus two. Oh, we got a 99 numbers. Delicious. All right. Okay.
And one plus.
All right. So we have a, we'll see this what, for A, for B, for C?
That would be part A,
All right.
and then part B is, gravity.
I got some points. Tell me, where the captain?
Yes, but we, we'll have to zero,
All right.
just plug those in with values.
So we got y is equal to I of ln of what?
For two,
And what's x?
one hour, so
Ooh. What doesn't mean? Ln of zero?
there, yeah,
I don't want to.
it'll give you one.
Yeah, one of them. So one, no, we need to change that point. Oh,
You want another one?
yeah, so I need 3/2. No, 3/4. That point, the point has to be three. Okay, we're in the middle of the math. Apply. We're not pretending, bro, we're engineers. What's the matter there?
Yeah.
What does it mean? Wow. Zero. So we're dividing by zero. We're crazy.
Yeah, so you did zero.
So if you are engineer in Edwards, you're like, okay, I have this equation. I can describe my what we talking about already? The streamline. You get this. What does it mean? What do you report?
Yeah, say, undefined.
Define. Okay.
That one.
Okay. What are your options? You're gonna throw away all the work that you have done? Or could you? That's an answer. Like you can do this, put it in a box. But if you're trying to get some info,
Explain it.
yeah, explain a little, or maybe work with this question,
Yeah,
because with that you cannot graph.
yeah.
So if you want to graph, because that's one of your questions, what will you do? If you want to graph this one, I know that this one should work. But this question we have like imaginary stuff, but don't worry about
Which one would grab?
it. What's the deal? So you know that you can like. What's yes, I have one hand. Please.
Think you could possibly estimate it by
Nice.
using a number close to one.
So not 3/4, like 3 over 3.9.
Yeah, something like that. But if it's not one, like something equals to one.
In that case, you're not dividing by zero.
Yeah.
So you technically you're getting like, so you kind of know what would happen. Or what's the tendency towards this guy, which is a really big one. But that's exactly what we can do. So what you can do is whatever the point doesn't exist, it's undefined. At least you can get at least more information, and then you report as, investors are happy. They're like, oh my god, we pay you $300 million, and at least we know that that's not the way. Like on the what doesn't, all right.
So you're saying that you should take a million point?
You can, I mean, you're saying this, so you're saying that point is undefined, but then what you can do is, yeah, just essentially say thing like that. You might get like a weird stuff, but that's possible.
Yeah.
The math matters. All right. Okay. Is that it?
Yeah.
Awesome. Any other questions? You too. Do you have any? Yes. Wow. Let's go. A lot of questions. All right. What's about what? Question 5.
Yeah.
Let's go. Okay. Let me erase this really quick. Can you give me the time?
Yeah, please.
Oh.
2:40.
Okay, we have. Good. Good. All right. So. So we want what? Okay, we're giving the velocity vector, which is okay. Let me do weird stuff with that. So 1 over x. Let's say 9 what? So oops. 7. Let's see this. All right. What happened? What are we doing? Okay.
So we are given a formula plus.
Yeah, acceleration formula. So we have acceleration is equal to the derivative of the velocity with respect to time.
Plus
Uh-huh.
velocity times gradient of velocity.
All right. It's not, this is it's called a
I computed the acceleration by saying that our derivative of velocity with respect to x is 0.
so you're saying that when you have velocity and you derive yeah, it's equal to 0. Why? Exactly. Precisely.
And the second term
The second term, yes, that one. Okay.
is multiply our vector
Yes.
times the derivative of this component.
Let's study them. So you're saying that that's a gradient, right? Right? The one in the of this guy? That's is that the gradient? What is it?
What do you mean?
Like what? No. I'm asking what are we doing to the vector? Like if we're like this, what are we doing here? What what is this called and what do you do? Because that, if you don't know, if you do know, you can proceed.
If there was gradient, would be like, the rating into the components. That's one.
Yes. So it will be like matrix for the gradients. What is that? Well, that's the curve. Look at your notes. What does your note? What do they say? The gradient? Does the curve? What is it? Divergence. That's another. Okay. Divergence. Okay. That's a good stuff. What is it?
You're saying that the term that you feel like the squared out, that's the divergence?
No, this is the like
Yeah.
nabla dot product vector. That's the variance.
The whole term?
Mm-hmm.
Like the vector dot product of the gradient 1 second.
Dot product of nabla.
It's the triangle times the vector.
Yeah. Yeah. It's good that you guys have that. That's the reason I was asking.
Yeah, how do you define the gradient?
The gradient. I think a way to define it is like this. You can look that up alone because there are different ways of defining the gradient.
That, yeah, that's right. That symbol.
That's the reason I was asking.
Yeah, that's how.
When you're doing gradient, is this. So you get f of x, the derivative with respect to x, f of y, whatever the vector is derivative of x, and for z, the partial derivative with respect to x, and then you do the same for all the components. That's it. It's a tensor.
Yeah.
We don't have a tensor. All right.
I did,
Huh?
I made a mistake, so I'm looking at it.
All right. So what are we doing now? So we have the divergence of B, right? Divergence of B. That's another way, right? So what's the divergence? What are we doing to this little bit? What? Why are we the derivative? What's the derivative of x? So we take the derivative of x here. First one, right? What's the derivative there? Yes.
X minus. No, yeah.
All right. Good. What about this? A 9? Oh, 9 y to respect to what? So we got nice. Yes. What about the third guy? 14C. All right. 14C. All right. What do we do now? So we have this part, this. Two of them. Yes. What is? Yes. All right. So good. So we have element x, element y, element c. And the same here. We have element x, element y, and c. So what do we get? So we're multiplying what? This with 9? No. All right. So the time was. So what do we get here?
And.
So -1 divided by 16, okay? X to the minus, yes, 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 yes. Oh, okay, what else?
And 81, what?
81, yeah, 81. What? Okay,
Yeah. What do you need? I'm sorry.
it's 70, 98.
Yeah.
98, Z,
See.
all right. But is it a vector?
No, I think that's someone.
Oh, good, we can scale it. Good. So we'll do this. All right. Is that it? Is that it? Oh, so this guy's here. Alright, so we get that the acceleration for my vector is minus x to the third or 16 plus 81 y plus 90 a z. Good.
Also, yes, you put the arrows, you have readings. And that's an investment, right? I thought the divergence would be scalar, because I thought divergence would be alpha. Like that's the one that is actually better. So that's why I thought that was great, because great just.
Divergence do give you a scalar. Yeah.
Yeah, but right there you have your vector equation.
So in that case, I was wrong. It's a product. This. How do I fix it? Because as you're saying, which is right, I'm checking it right now, and they're correct. This is wrong. Or we can fix it easily. What do we do? Yeah. So we have basically we basically get this vector multiplied by that.
Okay.
Which is basically a longer expression. So we so it will be this. Nine, it's another one. No, it's 9. Was 14. All right. You want to plug the numbers? Yeah.
What are you going with?
We are going over calculating acceleration of a vector.
It's like 5 by. Okay.
So then we have oh. 1 over x. So we can do a is over. Ax is equal to basically this times 1 over x. We got 1 over 16. That's 3. And we get a 1 y. 8 c d. All right. When I calculate the acceleration for that specific component, you also need to do like a You look confused. No, I will. Do you have any questions?
So I'm trying to look at the convective equation and it's supposed to be about product that you have before. So I'm just trying to understand the divergence between it, whether that should actually be a vector of the gradient time the dot product single vector. That was my assumption. That's why we were lost. It's just understanding the original equation we have.
Let's see. Check it up. We have 6 minutes. Remember what lecture is it? Lecture 7. Okay. So. Oh yeah, sure. Right. So we have here. That's all.
We have the
Single consideration. Solution. So basically, we have the curve.
on the very right hand side of where it has the no. Yeah, that looks like it's the delta, the triangle V is supposed to be the vector of the partials for each one. D over dx, D over dy.
That's what we have. Yeah, it is what we have.
So I think it's a non-product of the gradient times the velocity.
In that case, we get a pencil. It is a grid. So we don't. So we get dx. Yes, we take velocity. So we're doing a dot product of velocity and a matrix of intensity.
Negative scaling.
And that would give us, should give us a, I'm not sure. Should give us a vector. Do you figure it out? Do you figure it out?
First, I computed in green. Okay, but I wasn't sure. But it should be like this. I think the next floor of convention. So using previous, of my. These are not the things that most of the documents of the center are still.
Yes,
So when you apply it, it will.
so we get a tensor
And it.
another way. So we do calculate a gradient. Okay. The gradient is what we said before. Right? So we get Vx y. It's not a dot product. Okay. It's a multiplication between a tensor and then. We went over this. We didn't go over this, but what he said that we should review this. I think it was the second lecture that I said, okay, remember reviewing integration of vectors and matrices. Okay. So there's some multiplication of two matrices. A vector. That makes sense because I was like, sure, but I don't get why we get this.
So what's the definition like that?
The divergence is a tensor. A tensor, basically what it tells you is the change of that vector with respect to of a variable. For example, here will be the first component, like all the components with respect to x, then all the components of the vector again. With respect to y.
Yes.
It was kind of bad, but I confused you guys a little bit. I was poking you with it.
Well, I think it's, well, I know it's all wrong, but.
Now it checks out.
So what would be the result if we find out the actual? What should be the result if we have of values or will be one factor?
So Carlita was saying that when you multiply this tensor, there's a bunch of entries are 0, so you get a vector. You don't get a vector. Unfortunately, it's 3 of. Huh? Oh, you have class of 3? In Turlington? Wow, you really wanted to come here today. Oh my god.